Hi, in this video I'll be discussing the electrostatic properties of a conductor. I hope you like it, and if you do like, subscribe and share the video, as well as ring that notification button bell so that you get the most up-to-date information about when we are putting out the videos next. Okay, so let's get started. Okay, so electrostatic properties for a conductor. Simply put, there are quite a lot of properties, but very important to understand. The first one is very simple. The electrostatic field inside a conductor is zero. This is a very important one and really intriguing. So, electrostatic field inside a conductor is zero. What this means? What this means is, for a conductor of any shape or size, right? For a conductor of any shape or size, when we look at the inside, right? When we look at the inside, the electric field is zero. What this means is that there is no motion of electrons inside when the field is zero. Okay, let me explain how we get to this conclusion. Suppose I have a metal piece, a random metal piece like this. Okay, if I wanted to check if the electric field inside was zero or not, what will I do? I will use a Gauss law to just make a Gaussian surface inside, and I will now see what is the flux that is moving out of it, and obviously what is the charge that it is encapturing. Now, for a electrostatic field, that means at a static point when the charges have distributed themselves and everything is completely happened, it is stable, it is static, nothing is moving. That's when we are talking about. At that time there is no charge inside, right? There are free electrons that are present, but as a whole, in totality, there is no charge inside. When there is no charge inside, how can there be a flux or an electric field inside, right? And that's why we can say that electric field inside a conductor is zero. When the electrostatic field inside a conductor is zero, obviously in a static condition, right? So this is very important, and of course we can take this Gaussian surface, make it bigger as well as smaller, and so we can always check. So suppose if my charges were like this, right, after I've induced a charge, it kind of balances each other out, goes on different paths, but now it is in static condition. That means it is balanced and there is no movement of charge. When there is no movement of charge, in totality, the center, in the middle, the charge is zero. There is no additional charge that is there. I can make the Gaussian surface bigger or smaller and get the same result. Okay, very important to understand and comprehend. Next one is, on the surface, electric field is perpendicular. Electric field is perpendicular to the surface at each point, at every point. Again, taking a very random conductor, just any shape, right? Just any shape. Very important. When I take any shape conductor, what I am saying is the electrostatic field, when the charge has distributed itself, at every point, the electric field needs to be perpendicular to the surface. It needs to be perpendicular to the surface. Why is that? Because I can very easily prove this by using a opposite example. What if it wasn't perpendicular? If it wasn't perpendicular, suppose here my electric field would have been this way. Now if the electric field would have been this way, I can have a component like this as well as like this. That means I would be able to have a component of the electric field at the surface. When I have a component of the electric field at the surface, the charge will start moving because of it. So the charges around that point, the charges surrounding that point will start moving. It is almost like that I am trying to push that the person next to me, and that is exactly what's going to happen over here as well, right? So that's why the electric field, because we know that in an electrostatic uh, field or a position, this can't happen. And since this can't happen, the electric field has to be perpendicular to the surface. Got it? So that there is no component of the electric field towards the surface. Right? So once we understand this, again, very important to understand the reasons, because if we don't understand the reasons as to why things are happening, then we are just memorizing these things, which is not the point of this exercise in these videos. The idea is always to teach you how to think. Why is something happening? Why is something else happening? How are things related to each other? And so on. Now, the next one, inside a conductor. Inside a conductor, there is no change in the static situation. There is no excess charge in the static situation. Okay, let me rephrase that. Inside the surface of the charge conductor, inside a conductor, there is no excess charge. Okay, again it comes from the same concept as if there was an excess charge. If there was an excess charge, what's going to happen is it will create an electric field. If there was an electric charge, it will create an electric field which will push or pull other charges around it. That means it won't let the static position remain static. Again, we do not see that happen in a conductor which is just there. We do not randomly see that a charge passes by, right? So even in a charged conductor, okay, so we do not see it in a neutral conductor, but we do not see it in a charged conductor as well. So suppose I have a sphere which is charged, right? It's charged all through. Now suppose if there was an excess charge in the middle. If there was an excess charge in the middle, what is this going to do? It is going to push the charges around it away, creating a small electric current. But we do not see a small electric current inside the sphere randomly in a charged sphere. That's why this does not happen. By observation we know that this does not happen. So if it can't happen, that means there is no charge in the middle. That means there is no possibility of a charge in the middle, and so all the charge is always on the surface of a conductor. Again, very important, all the charge is always on the surface of a conductor and not inside, and we'll again see how. Okay, next next the electric field is constant on the surface as well as inside the surface. Again, very important, electric field is constant on the surface and inside the conductor. Okay, this comes from the fact that electric potential over here is the same everywhere. Okay, that means if I take a charge from the surface, or if and I move it across the body of the conductor, I do not have to do any work. Of course, this thing comes from the first and the second the points that we discussed. One, that the electric field has to be perpendicular to the surface, and second, that the charge or the field inside the conductor is zero. So if the field inside the conductor is zero, there is nothing that I am working against, and therefore the work done by me inside a conductor is zero, and on the surface it's the same, right? Next is very simply extensions of this onto electric potential, which is the electric field at the surface. First of all, is sigma upon epsilon. Electric field at the surface is sigma upon epsilon naught n cap. N cap stands for the perpendicular. How did we get this? Let's try. Let's make a conductor like this. I'm going to make a pillbox. Pillbox is simply a very small cylinder, and that is the name we are giving, right? So this is the pillbox. Now obviously the pillbox is a Gaussian surface and it is cutting the conductor at this point. The solid line shows the conductor. Okay, so that means some of it is inside and some of it is outside. Why have I taken it this way? Because the charge only resides on the surface. So I want a bit inside and outside so that I know which way my electric field is. Now if my charge is here and my electric field is perpendicular to the surface, I am obviously making the pillbox in a very small size area, and so I can assume that all the electric field in that area is in one direction, right? That means electric field in that area is perpendicular to each other, and that is our assumption. So now electric field, or rather by Gauss law, flux is equals to sigma, flux is equals to charge upon epsilon naught. So I am going to use Gauss law here. What is the flux? Flux is only moving from the top surface, right? That is the only surface through which it can go, because there is no electric field inside. So nothing can go inside, and of course because the electric field is perpendicular, there is no electric flux moving this way of the pillbox as well. That means electric field into the area of the pillbox, right? Into the area of the pillbox on top, which is equals to Q. Q is the charge, the surface charge, right? Now surface charge, let's call that surface charge as sigma, right? So sigma is essentially surface charge density. That means charge per unit area, and of course charge per unit area into the area will give me the total charge in this area upon epsilon. We can see the area cancels out, so I have electric field as equals to sigma upon epsilon naught, and the n cap comes due to the perpendicular nature of the electric field, perpendicular to the surface at every point. And this is a really important, again very important result. Okay, now the last thing is electrostatic shielding. And electrostatic shielding is very simply, if I have a conductor, since there is no electric field inside, we've already done this in for the first point. Because of that, I can keep any important or very I can keep instruments which are very sensitive in nature, right? Which get affected by electric fields from even the slightest of electric fields outside, right? So we can keep them here and it will protect them from external electric fields or additional electric fields. So this idea is also used to protect things like mobiles and like hard disks and whatnot from unnecessary electric fields that might be present or unnecessary radio frequencies that might be present in our surroundings. Okay, so the concept of electrostatic shielding is that because there is no electric field inside, it essentially protects any field from coming inside, and I can keep a tool or whatever that I want to protect over here. Okay, so that's it for this video. I hope you liked this video. If you did, please like, subscribe and share with your friends and family so that you can discuss these things with much more clarity as well as think better together, right? Do comment with what you want me to cover next, as well as any doubts that you might be having, and I would be happy to respond to them as and when possible for me, as quickly as possible for me. So till then, I'll meet you in the next video.